Hello, so this is the first chapter 2 review, and I wanted to start by showing you that there is a module that is important that you are aware it exists there. On top of the chapter 2 module in the Canvas homepage, there is the calculator module, and in there you have the scientific notation, display mode, logs, and anti-log. So you want to look at that playlist, and if I go to it, there is 4 videos. So depending on the calculator you have, if you have the TI-30X2S or the TI-84 or TI-83 or TI-84 plus, TI-83 plus, you will have help in that playlist. We don't use the log function, so it's mainly the 2 video that are on scientific notation and display mode. So you want to watch these for sure. It is important that you know how your calculator works. Very important. So please take the time to watch these videos if you have these calculators. And if you need help with your calculator, show me a picture of your calculator, and then I can help you know how to do the scientific notation and change the display mode. Or the best would be to do that in a Zoom meeting. So we'll start the chapter 2 review, and with the first question. So chapter 2 is on measurements and calculations, and it's to prepare you to do what we call in chemistry stoichiometry. So all kinds of calculations where you have conversions of units. And this chapter is preparing you by having you practice converting between regular units of volume, length, mass, etc. And when you do measurements, you have to pay attention to significant figures. So from now on, you will be expected to pay attention to significant figures. And there are details, but there are details that may throw off your answers, especially on sapling. And so it is important to learn that correctly, because it will save you from frustration. So let's practice this. The first number here, 25,400. How many sig figs in that number? So significant figures is long to say, and we say it so many times that when I say sig figs, it means significant figures. So how many sig figs in this number? So what you have to know is that when you have zeros at the end, to the right of a number, these zeros are not significant if you do not see the decimal point. And here we do not see a decimal point. What I mean by decimal point is this, right? We do not see that, it's not there. So that means those 2 zeros are not significant. And so this number will have only 3 significant figures here because of that. So now let's write this number in scientific notation. So we know the decimal point is there, even though it's not shown. And so you will move the decimal point 1 time to the left, another time to the left, then behind the 4, and then behind the 5. And you will stop between the 2 and the 5. And why do you stop there? You stop there because it's a number between 1 and 10. Always reach for a number between 1 and 10 when you're changing a number into scientific notation. So 2.54 is between 1 and 10. The zeros are not reported again because they are not significant. So in scientific notation, you should only see the significant figures. And so here, and then you times 10. And here, the exponent should be the number of times you've moved to the left. And we have moved 1, 2, 3, 4 times. 4 times. So it's going to be a 4. And now you have to decide, is it a positive 4 or a negative 4? Because exponents can be positive or negative. And here, because, so please do not decide, if it's positive or negative on the fact that you move to the left or to the right, because that's going to be very confusing when you are, going from regular notation to scientific notation or the reverse, and you will not know anymore which is which. What you want to remember is that numbers that are large, like this, 25,000, should have a positive exponent. And so the 4 here will stay as a 4, and it's a positive exponent. So that's it for the 1A. Now let's do 1B, 1.60. Here again, there's a 0 in the right of the number. And we just said above that the zeros are significant if you see the decimal point. And we do see the decimal point there. So that 0 to the right will be significant in this case, right? We are talking about zeros to the right. So if it is significant, then that's 3 sig figs again in that number. And in scientific notation, so normally you move the decimal point until you reach a number between 1 and 10. But here, this is already a number between 1 and 10. So it's going to stay the same. And here the 0 needs to be put here because it is significant. So you need the 0 there. And because we didn't move the decimal point, so it's going to be an exponent of 0. We moved 0 times, right? And if you do this 10 to the 0 in your calculator, you will see that it is equal to 1. So 1.60 times 10 to the 0 is equal to 1.60 times 1. And that's again 1.60. So that's the scientific notation for this number. 1C now. Oops. Sorry. So 0.001285. So this time the zeros are to the left of the number. And even though we see the decimal point, these zeros are not significant. Be very careful here. They are not significant until you reach a non-zero digit. And here we reach the non-zero digit when we reach the 1. Anything before that is not significant. So there is 4 sig figs there, the 1, the 2, the 8, and the 5. So when you write this in a scientific notation, you want to move the decimal point, and you will move this time to the right because you want to make a number between 1 and 10. And so for this, you need to go. So 1 time here, 2 times, 3 times when you reach between the 1 and the 2. So you report all digits here, 1.285. We have a number between 1 and 10. And then you multiply by times 10, and the power should be the number of places you moved. And we've moved 1, 2, 3 times. So it's going to be a 3. And then you decide, is it a positive exponent or a negative exponent? And here we started with a very small number, right? A number much below 1. So that means it's a negative exponent. Yeah, let me add the fact that negative exponent, so like here, means that you're taking this number, 1.285, and the times 10 to the negative 3 means you are dividing 3 times by 10. And then you get back your regular notation. So if you take 1.285 divided 3 times by 10, you get back your regular number. And when the exponent is positive, you multiply by the exponent number of times by 10, and you multiply. So for example, here, you take 2.54 and you will multiply 4 times by 10. So times 10, times 10, times 10, and times 10, 4 times. And you will get back your original number. So that's another way also to remember, negative exponent means you divide by 10, and so it's going to be a small number. Okay, so 1D. again, we have numbers here to the left. And even though we see the decimal point, those digits are not significant. Those zeros are not significant until you reach the 5. Once you reach a non-zero digit, what comes to the right will be significant. So that 0 to the right is significant because you see the decimal point and it is to the right of a non-zero digit. So that means you have two significant figures in that number. So 2. And so let's write this in scientific notation. So we will need to move this decimal point to the right. So one places, 2 places. So until we reach 5. And because the 0 is significant, so you need to show 5.0 times 10. And we said we move 2 places to the right. So the exponent will be a 2. Now we need to decide, is it positive 2 or negative 2? And this is clearly a small number. So it's going to be divided 2 times by 2. So it's going to be negative 2 for the exponent. So you see how, in scientific notation, all the digits reported, in the decimal part of the scientific notation are always the significant numbers. So question 2 then, convert each number to its standard form. So we have these 2 numbers here. And they are in scientific notation right now, right? And so we want to bring them back to standard form. And so notice how there is many ways to talk about the standard form. It can be regular notation. It can be decimal notation. The calculators tend to call it floating point notation. All of these are, meaning the same thing. It's just the way we are used to see numbers. So here we need to look at the exponent. It's a negative exponent, which means you will divide 7 times by 10 to get the number in standard form. And so if we divide by 10 7 times, you want to make this a small number. So the 1.00 should become a small number. And so you will move the decimal point 7 times to the left, to make it a small number and add a lot of zeros to the left. So, 1, 2, 3, 4, 5, 6, and the 1 will be at the 7th place. Let me make sure. 1, 2, 3, 4, 5, 6, 7. So there we go. I moved the decimal point from here, from the right of the 1, and I moved it, between the 0 and the 1, etc., between zeros 7 times, right? And so I get this. So let's think about sig figs here for a minute. How many significant figures there is in this number? There is 3, right? Because the decimal part of the scientific notation shows all significant figures. And here there is the 1 and then the 2 zeros. Those zeros are significant because you see the decimal point. So we have 3 sig figs. This is important here because when you do write this number now in standard form, you need to show that there is 3 sig figs. And right now there is only 1 sig fig, and that's the 1. So you need to add 2 zeros to the right to make it 3 sig figs. So that's why the proper standard form for this number is this, with the 2 zeros, reported back. And so that's 3 sig figs, and then it's 10 to the negative 7 there. So think about that when you're doing this type of conversion between scientific notation and standard form. So let's practice with this one now. 6.886 times 10 to the 5th. So we have a positive exponent. So that means we will multiply 5 times by 10, this number. So That means the decimal point, you will move it to the right because you want to make this a number, a larger number. Like if you are multiplying by 10, five times. So 6, so 1 time, 2 time, 3 time, 4 time, 5 times. This way I've moved 5 times the decimal point 5 times to the right to make this a larger number. And this way I have, the regular notation here. So the question may be, oh, do I show the decimal point or not here? Well, the answer is no, you should not show the decimal point. Because if you do show the decimal point, it will make those zeros significant. But they are not. If you look at your number in scientific notation, there is only 4 significant figures there. So 4 significant figures. So you want to keep it 4 significant figures. And so that means do not make those zeros significant. And so do not show the decimal point. Another detail that is very important here to remember. And so in America, we use commas to show the thousands place, millions place, billions place. So here you can put the comma if you want, or not, it's okay. So that's the standard form for this number. So question 3, which number in each pair is larger? So we have these 2 pairs of numbers. The first one, we have numbers that have a negative exponent, right? You notice how it is negative exponents. So the first thing when you have numbers in scientific notation and you need to compare them, look at the exponents. So here they're both negative, so you need to compare the exponent themselves. And when it is negative, remember that it means, here, negative 6 means you divide the 8.6 6 times by 10. And in 10 to the negative 2, it means you divide the 6.3 2 times by 10. So whatever the decimal part is, 6.3 or 8.6, it doesn't really matter. At this point, the difference is in the exponent. And here, dividing 2 times by 10 or 6 times by 10 really tells you that this number will be much smaller. And so I will highlight the one that is larger. So which one is larger? Let me just emphasize this means this is the one that is larger, right? Because you're only dividing 2 times by 10. So now, if you have positive exponents, remember that a positive exponent means you multiply here 8 times by 10 and here 4 times by 10. Again, you don't need to look at the decimal part. It doesn't really bring anything when the exponents are so different. Only looking at the exponent is enough. And here, multiply 4 times by 10 will not make a number as big as multiplying 8 times by 10. So again, this number will be the larger one out of the 2. So that's, you see how scientific notation here simplifies the comparison. So question 4, complete the sentences. In multiplication or division, the final answer is written so that it has the same number of as the measurement with. And so here we are missing words. And so it's about the rule to follow when you're multiplying or dividing. And when you're multiplying and dividing measurements, where significant figures matter, you want to keep the same number of significant figures. So for multiplication and division, it's significant figures that matter, as the measurement with the least number of significant figures. And this is really a rule you need to learn by heart. This is very important to remember that. And then we will practice in question 5. So So it is important here for multiplication and division. You want to keep the same number of sig figs as the number with the least number of sig figs. As the measurement, I should say, with the least number of sig figs. But unfortunately for addition and subtraction, it's a different rule. And the final answer is written so that it has the same number of, and it's not significant figures here. It's decimal places. Decimal places or, significant digit. Both are correct. No. Decimal places. As the number with, let me add the list, with the least number of decimal places, or it can be sometimes there's no decimal places, and in this case you have to pay attention to the least precise digit in your number. So that's not always decimal places. Sometimes it's the least precise digit, which means, for example, if you have, for example, 1,250, the least precise digit would be the 5 here, right? The 0 is not significant. And so the 5 is the least precise digit. And so that means you would need to round to the 10, because that's the 50 here is to the 10th place, right? So that's what it means here. It's easier to understand with the number of decimal places. So we'll practice that here. So let's do question 5 then and practice these two rules. So first, let's practice with the multiplication here. 49,682 times 0.80. So this is a multiplication, so we need to pay attention to the number of significant figures. So how many significant figures do we have in 49,682? We have 5 sig figs, right? And in this number, how many significant figures? So remember how the 0 to the left is not significant until you reach a non-zero digit, and then everything after is significant. So here the 0 to the right is significant, and so we have 2 significant figures here. So we want to pay attention to the number of sig figs, and it's going to be 2 here, the least number, right? Out of these 2 numbers, the least number is 2. So you do the calculation in your calculator, and your calculator doesn't know about sig figs, so you cannot trust it for that. You have to think about, okay, the answer is 39,745.6. So that's the calculator answer. Everybody usually can do that. But then you need to think, okay, I need to keep 2 sig figs. So 2 sig figs, and you start counting from the left, right? Counting from the left. So I keep the 3 and the 9. So that would mean 39,000. And then what comes after the 9 is a 7. So that means you need to round up. So that means the 9 needs to become a 10, and 39 needs to become a 40. So it's 40,000, because everything after that, becomes 0. You need to show that it's in the thousands place, right? So 40,000. However, if you keep it like this, it's only 1 sig fig, right? So that's not enough. You cannot keep it like this. You need to show 2 sig figs. And sometimes the only way to show 2 sig figs when you have zeros to the right like that is to use the scientific notation. So we need to put this number in scientific notation to show only 2 sig figs. Because, right now it's only 1 sig fig. And if I were to put a dot here, the decimal point, I would show 5 sig figs, because all zeros would be significant. So it's either 1 or 5. There is no possibility to show 2. So that's why you have to write this number in scientific notation where you show 2 sig figs and then times 10. And here we move from between the 4 and the 0, 1, 2, 3, 4 times. So 10 to the 4. And that's a positive exponent because we are multiplying 4 by 10 4 times. And so that's the final answer here, right? This one was the calculator answer. This is how you would round. And actually, I don't show the dot here. But this shows only one sig fig. So then you need to use the scientific notation. So this is very tricky. And actually, sapling learning is, expecting you to show scientific notation whenever, you cannot show, it cannot accept when you are using the decimal point. It will not take that. So you need to show scientific notation with sapling more often because of that. So now we will do a subtraction. And so the rule is different. As you see above, it's the number of decimal places or the least precise digit that will matter now. So we have 21 and 0.88. So we said it's a subtraction, so it's the number of decimal places that matter. So let me emphasize that. And here in 0.88, we have 2 decimal places. We would stop to the, so that's the 10th place. That's the 100th place. That's quite precise. But here, 21, there is no decimal point. But we know the decimal point would be here, right? If we show it, it would be here. And so this is precise to the ones place. That's what it means here. It's precise to the ones place. So that means we will need, to the ones place. We need to stop to the ones place. That's what this rule above, the least precise digit, that's what it means. So let's do the calculator answer. So 21 minus 0.88. And remember how your calculator doesn't know about, these rules. And so you have to think about them each time. So that's the calculator answer. And now we need to round to the ones place. To the ones place, that means here to the 0. So that means 20. What comes after the 0 is a 1. So you keep the 0 a 0, right? When you have a number below 5 that comes after the last number you keep, you round down. If it's above 5 and above, you round up. So here we round down and we would stay like this, right? But if you keep it like this, it's only showing, one sig fig, and it shows a precision to the tens place, not to the ones place. So that's not correct. So the way to show that it's to the ones place, you need to add that 0, the decimal point, I mean, right? This is important here to show the decimal point. Why? Because the decimal point makes that 0 significant. And it shows that the precision, it's up to the ones place, not to the tens place, but up to the ones place. So either like this, or again, use the scientific notation. Here on paper, you don't need to use the scientific notation, but I want to warn you that sapling learning will not accept this as correct, unfortunately, and you will have to use the scientific notation. So 2.0 to show the two, to the ones place here, times 10 to the 1, right? It's 1 time that we move the decimal point to the left between the 2 and the 0. And so that would be the final answer in sapling, for example. It would only accept that kind of answer. Okay, let's do these operations here. Notice how we have addition and subtraction in parentheses to do first, because we follow the Pemdas rules, right? Pemdas means parentheses, exponent, multiplication, division, addition, and subtraction. You have to do the operations in that order. And here we have parentheses, so we need to do this first. And it's addition and subtraction, which means we will use this rule about the least number of decimal places or the least precise digit. Then, once we have our intermediate answer, and you have no choice but to show your intermediate answer on paper when you do this, and then divide by 0.98. Then it's a division, and then you will apply the first rule here. So there is 2 steps, right? And you will have an intermediate answer that you have to show. So let's do this calculation in the calculator first. So 2.7518 plus 9.1 minus 0.354 equal. And so the intermediate answer is 11.4978. And then you keep the rest the same for now. Okay. So this is the intermediate answer. That is the answer of what's in the parentheses. We need to, even though we will keep every digit that the calculator gives, you notice how I kept everything from the calculator. You need to decide if you were to round, where would you stop? Where would be the least precise digit? So in the first measurement, there is 4 decimal places. In the second measurement, there is 1 decimal place. And in the third measurement, there is 3 decimal places. So the least number of decimal places is 1 from the 9.1. So that means the intermediate answer for this addition and subtraction needs to be kept to 1 decimal place. So I'm going to underline this to remind myself I need to stop the precision there to the 0.4, which actually would be a 0.5 if you were to round, but you do not round. It is important here to not round intermediate answers. However, you need to do this step of estimating where you would round if you were to round. So next, you keep that number and divide by 0.98. The calculator answer is 11.732448, etc. There's too many digits, and we know we won't need all of this, but that's the calculator answer here. And I've used all of these digits, right? I did not round. This is important because it can change your final answer if you round early. So now we have a different rule because we are dividing. It's the least number of significant figures that matter. And here we have, if we were to round at 0.4 or 0.5 here, 11.5, we would have 3 sig figs. In the second number, we have 2 sig figs only because the 0 is not significant. So we need to round to 2 sig figs. So then you keep, out of this, you keep the 1 and then the 1. And that's already 2 sig figs. So you need to stop there. What comes after the 1 here is a 7. So you need to round the 1 up. So it's not going to be 11, but 12. And so that's 2 sig figs. And that would be the final answer for this calculation. So notice how you need to calculate the intermediate answer, estimate how you would round, but do not round. And then when the rule changes, adapt. Keep here, needed to estimate the number of sig figs. That's 3 here, but 2 there. So you keep 2 sig figs in the end. One more practice with this mixed operation calculation here. We have this number in scientific notation divided by, and then we have an operation to do in parentheses, and that's an addition again. So we need to do what's in parentheses first, right? You cannot divide the numerator with the first denominator and then add the rest. It's not correct. You need to do what's in the parentheses first. So we need the intermediate answer, and so we need to rewrite this and then find the intermediate answer. So in the calculator you do, actually, let me think. You need to show these numbers in a regular notation, because this is possible here. 10 to the 2 and 10 to the 1 can be shown in a regular notation, and that will help us see, the least number of decimal places or the least precise digit, because this is an addition. So we need to pay attention to the least number of decimal places or the least precise digit. So convert 1.43 10 to the 2 to a standard notation. So the positive exponent means you multiply 2 times by 10, and so move the decimal point 2 times to the right. Oops. So I'm going to do that here. So 143, that's what it is. And then this one, you multiply 1 time by 10. So you move the decimal point 1 time to the right, and that's going to be 45.1. You need to see that, because then you need to see which one is the least precise, right, digit. And so we will need to rewrite this and calculate the intermediate answer, and then estimate where we round, or if we were to round, where we would round. So 143 plus 45.1, that's 188.1. That's the intermediate answer of what's been added in the parentheses. So the least number of decimal places here, because it's an addition, so you need to look at that. Here we have precision to the ones place, right? This is where you have the dot. So this is precise up to the ones place. And here it is precise to the 10th place. So the least precise is to the ones place. So that means we would need to round, if we were to round, to the ones place. So I'm underlining the 8 here to show that I would stop here if I were to round. But I do not round, I keep everything to do the calculation. So let's do the calculation and have the calculator answer. 9.762. So second EE key in your calculator, so that you use the scientific notation. So second EE key, -3. This tells your calculator that 9.762 10 to the -3 is one number, and it will keep it all together. Divided by 188.1 equals 0.000051898. Yes, because this is a small number, and even though we are and we are dividing, so we are making it even smaller. So 4 zeros there, yes. So that's the calculator answer. Because we are dividing here, we need to pay attention to significant figures. And here, if we were to round at 188, we would have 3 sig figs. And here we have 4 sig figs. So the least number of sig figs is 3. So we need to keep 3. All these zeros to the left are not significant. So you start counting from the 5, 1, 8. That's 3 sig figs. So 3 sig figs there. So that would be rounded. Let me put it here so we see better. So 0.0000518. What comes after the 8 is a 9. So you need to round the 8 up. So the 8 will become a 9. And then you drop everything after that, because that's 3 sig figs there. And so that would be the answer to this second calculation here.
Ouais.
So this is a number with a lot of zeros to the left, right? And it's easy to, you know, miss, right?
Ninguém.
So you want to write this in scientific notation often when you have...
There's something wrong with this.
So this in scientific notation would be, so you move the decimal point 1 time, 2, 3, 4, 5 times to the right. So 5 point until you reach 5.19 times 10 to the 5. Here the exponent is 5 because you move the decimal point 5 times to the right. And it's negative 5 because you started with a small number. A small number, right, with a lot of zeros to the left. So it's, you know, 5.19 divided 5 times by 10. So that's the scientific notation, and it would be best to use scientific notation to avoid, you know, mistake and dropping 0 or adding a 0 by mistake. So as soon as you are, you know, as soon as you have more than 3 zeros, you know, to the left, I would use scientific notation as a rule. It's best practice.